Okay guys, we are discussing about full wave rectifier, and we know that there are two types of full wave rectifier. One is called central tape full wave rectifier, and the second one is full wave bridge rectifier. So we discuss about this central tape full wave rectifier in detail in our previous videos. So here in this video I will totally concentrate on this full wave bridge rectifier. So here I will give the name of my topic is bridge rectifier. First I will draw the circuit diagram of this bridge rectifier. So the circuit diagram it will take time. It's a little bit complicated. So I will draw so here we have so in bridge rectifier we are using 4 diodes. And we have a transformer, so this is a transformer, and here we have the AC voltage, AC output signal. So this will be 220 volt of 50 hertz. So this is the primary coil of the transformer. So here at this point I will call it P1 and this is called P2, and this is the secondary coil S1 and S2. Now the role of the transformer is it either step up or step down the output AC signal, the output voltage or output current, and the second role is like this transformer isolate this rectifier circuit from this output voltage, because here we have the isolation. Now we use 4 diodes here, and this is the circuit diagram. So we have 4 diodes. I call this one as D1 and this is D2. I call this as D3 and I call this as D4. Now 4 diodes are used here and they form the shape of a bridge, so that's why it is called a bridge rectifier. Now we have 4 points which are to be discussed here. One is point A and B, and the other one is point C and D. Now here at point A and B, opposite end of diodes are connected, because here this is the P side of diode D1 and this is the N side, and here this is the N side of diode D3 and this is the P side. So at point A, N side of diode D3 and P side of diode D1 are connected. Similarly at point B, this is the N side and this is the P side. N side of diode D2 and P side of diode D4 are connected. So these points are different because we have opposite ends of the diodes are connected at point A and B. Now point C and D are same end, because at point D both inside of diode D1 and D4 are connected. at point C, both P side of diode D2 and D3 are connected. So this is the P side and this is the N side. This is the P side of diode D4 and this is the N side of diode D4. This is the P side of diode D2 and this is the N side of diode D2. This is the P side of diode D3 and this is the N side of diode D3. So point A and B are different because opposite end of diode D1 and D3 are connected. N side of diode D3 and P side of diode D1 are connected to point A. Similarly, N side of diode D2 and P side of diode D4 are connected to point B. But point C and D are same end because both P side of diode D2 and D3 are connected to point C. Similarly, both N side of diode D2 and D1 and D4 are connected to point D. Now, a load resistance is connected to the same end. So the load resistance is connected between point C and D because these two ends are same, or these 2 points are same point. So we have to connect the load resistance here. This is the load resistance, RL. So we have to measure the voltage drop across the load resistance here. Now I will come to the operational principle of this diode. Suppose I will draw the figure again. Here we have diode D1 and here we have diode D2 and here we have the diode D3 and here we have the diode D4. So diode D1 and D2, opposite diodes have the same direction because D1 and D2 direction are the same because they are the same direction. Similarly, D3 and D4, they are the opposite diodes, so they have the same direction. Now this is P side, this is N side, this is P side, this is N side, this is P side, this is N side. Here we have the P side and this is N side, and we have the load resistance which is connected here, RL. Now these 2 points, I call it point A, this is point B, this is point C and this is point D. Now we have the transformer connected to this and we have, this is the secondary coil and this is the primary coil, and here we have the output source, AC source. Now suppose this is the output AC signals. So here we have the input, this is the input AC signal. Here we have the positive half, here we have the negative half, and this is omega t. Now suppose that the positive half cycle, this positive half cycle reach to the transformer or reach to this secondary coil S. This is S1 in and this is S2 in. Then from our previous knowledge, this will become positive and this will become negative. Now once this become positive, it means that this point A also become positive, and similarly this point B also become negative, this is negative. Now point A is positive, so this point A is connected to P side of diode D1 and N side of diode D3. So it means that this positive terminal is connected to this P side of diode D1, so diode D1 become forward bias, and diode D2, D3, it will become reverse bias. So diode D1 is, we assume that all the diodes are ideal, so if it is forward bias, it's behave like a short circuit. And this is reverse bias, so it's behave like an open circuit. Now if we look at this point, this is negative, point B is negative, and point B is connected to P side of diode D4 and N side of diode D2. So P side of diode D4 is connected to negative terminal. So it means that this will become reverse bias. It will behave like an open circuit, and this will become like here the N side is connected to negative terminal, so this will become forward bias and behave like a short circuit. Now I will plot this figure again. Now this is diode D1 and this is diode D2. This is diode D3 and this is diode D4. Now diode D1 is forward bias. It's behave like a short circuit. So there's it look like this. And similarly diode D2 is also forward bias. So it's also behave like a short circuit. While diode D4 and D3 are open circuit. So they are open. And here we have the load resistance. This is point A, this is point B, this is point C, and this is point D. And here we have the connection with the secondary coil. This is S1, this is S2. Now this is positive, this is negative. Now we know that current is moving from positive to negative terminal. So the path of the current will be from here to this way. So the current will move from this point to point A. Once it reaches to point A, then there are two paths for the flow of current. One is this one, A to D, and the other one is A to C. But the current cannot flow through this path, A to C, because this circuit is open. Here the diode is reverse bias. It cannot allow any current to pass through it. So it's open. So current cannot flow this path. So the path for the flow of current now will be this one. So when current reaches to point D, then again we have two paths for the flow of current. One is path DB and the other one is path DC. But this path is forbidden for the flow of current because here we have this diode D4 is reverse bias. It's behave like an open circuit. So the only path for the flow of current is now this one. At point C, the current cannot flow in this way because this is open circuit. So the current will follow this path. And when it's reached to point DB, then again it cannot flow through this path because this is open. So the current will flow here to this S1, S2, and then again from this one. So this is the path of flow when this positive half cycle reaches to this secondary winding of the transformer. So the path of the current will be from S1, this is S1, to A, and then from A to D, and then from D to C, and then from C to B, and then from B to S2, and then from S2 to S1 again. This is the path of the current. In the next video I will proceed further.